once we know this relationship, so we can estimate those difficult to measure product quality variables from those easy to measure process variables. Right. So due to the nature of a chemical and biochemical process, so the state of the secondary variable reflects the state of the process operation. So, for example, the liquid composition is often affected by pressure and temperature, and the biomass growth is linked to, for example, CO2 evolution and feed rate. So here we have this easy to measure process variable like temperature, pressure, flow rate. But the difficult to measure variable like the biomass growth, so they can be linked. And so if we find this model, we link those, so we can get those difficult to measure process variables. Right. So this diagram shows this the concept of this inferential measurement. So for example, this blue star represents this infrequent measurement of product quality. Okay, so suppose like you got 30 minutes this interval in getting this the measurement. Okay, so now I can see. So within this, so you got this measurement, and then until the next 30 minutes, you got the next measurement. So you can see you got this infrequent measurement. Okay, so this can affect your control performance. So if we have got a soft sensor, then from this soft sensor estimate, we can have a more like a frequent measurement of this product quality variable. So using this green curve, so we can control the quality variables. Okay. So this inferential measurement system, essentially they try to mimic this experienced process operator or process engineer. So when those experienced process operator engineer, when they run the process, so because based on their experience, so they can, for example, they from their observed value of those easy to measure process variables, so they can get some rough feeling of the product quality. So for example, in this in some process industry, the experienced operator, so based on those process process measurement, so they can roughly estimate the quality of the product. But the problem with this is you need this very experienced operator. Okay, and also the judgment can be inconsistent between different operators. So therefore, we need to get a more systematic approach to build this soft sensor or inferential estimate, inferential measurement. Okay, so basically this soft sensor and the inferential estimation, they depends on like a model. So this model relate the primary variable like product quality variable and some easy to measure secondary variable like temperature, flow rate, pressure, etc. Okay, now the modeling method can include those different methods. Okay, so the first one is a first principle model. So for example, based on mass balance, energy balance, reaction kinetics, so we can build these first principle models. But this model can be quite time consuming to build such a model because for the real industrial process, it can be quite complicated. There can be a lot of chemical reaction and some parameter may not be known. The second type model is a time series model. Okay, so we can build time series model and from process operational date. The third one is generally called the date-driven model or empirical model. So typically we use a multivariate statistical technique like partial least square and principal compound regression, etc. And also to deal with a nonlinear process, so we can use neural networks because neural networks are powerful for building this nonlinear data-driven model. So now I will briefly introduce some early days of research in soft sensor. So basically, I think the concept of soft sensor was started in like maybe around mid 1980s. Okay, actually Newcastle is one of the earliest research group to propose this approach. Actually, that group is led by the late Professor Julie Morris, and with Dr. Ming Tan as the main researcher for this in the early days of this soft sensor research. Okay, so I think probably Newcastle is the first group to apply this soft sensor concept to industrial process. So here, so we got this, for example, in this 1985 Canadian Chemical Engineering Conference and 1988 American Control Conference. So in those conferences, they report this industrial application, large scale industry. Okay. So there's this paper by Dr. Tam in Journal Process Control. So this one, I think this one is the first journal paper on soft sensor for process control applications. So you can see this paper is the first paper in the very first issue of this journal process control. Okay, so this paper is highly cited by researchers in process control area. So one of the very first application is so here we apply a soft sensor to this adaptive estimation in an industrial 120,000 liter feedback penicillin fermentation reactor. And there's another one is 140,000 liter continuous protein fermentation process with ICI. I think this one is Dr. Ming Tan was behind this research. And also nowadays, it's a soft sensor actually is like reinvented. So actually that's words from the late Professor Julie Morris, because he's like find this I mean this soft sensor concept like started in Newcastle quite many years ago, but now it's like reinvented into this virtual process analytical technology tools. So it's virtual PAT tools. But actually, I think they are virtually they are the same, but with a different name. So this picture shows this the first industrial application. So they produce this protein, this artificial meat, is corn. This brand of the I mean for the vegetarian. Okay, this product. So that's with ICI back in 1986 around that time. So you can see the work is mainly done by Dr. Ming Tan at that time. So you can see this in this plot. You can see this solid curve represent offline measured biomass. So you can see they got 8 hours sampling time. So you can see within this so every 8 hours you take one measurement. So clearly, like it's difficult to use this for online control. Okay. So with this soft sensor, so you can see we have this dashed line. You can see with the dashed line. So between this 8 hours period, so you can have a more frequent estimate of the product quality of the biomass. Okay. So with this frequent estimation of biomass, so you can control the quality much better than just rely on this infrequent hardware sensor. Right. Now this picture is taken from this industrial 4.0 for chemical industry. Okay, so you can see now they call this virtual sensor. Actually, it's just soft sensor. but so it's like reinventing this self sensor with a different name. So now you can see in this industrial 4.0, they try to utilize this self sensor concept. Okay, so combined with a hardware sensor and with those more process analytical technology, so you can provide more improved process control. Right. Okay. So now these slides just summarize some modeling techniques, because the key technique for soft sensor is model. Okay, you need to get model to link this easy to measure and difficult to measure quality variables. Okay. So there are different techniques we can use for this soft sensor development. So the first type of technique is called regression-based modeling. Okay. So this one is quite quite widely used. Okay, so we can have a multiple linear regression, principal component regression, partial least square regression. Okay, now those are linear techniques. Okay, so try to build a linear relationship between the process variable and the product quality variable. But sometimes the relationship can be nonlinear. Okay, so in that case, we need the nonlinear version of those regression technique, like for example, weighted regression, fuzzy, partially square, neural networks, etc. The second type of model is input, output, and state space based modeling. Okay, I think the very early research on this soft sensor by Dr. Tam, so they use this state space modeling technique. Okay. So the estimator employ either an input-output or state space process model. So we can use this kind of common filtering, recursively square those approach to update those models and to get inferential estimation. To deal with nonlinear process, so the most popular approach now is a neural network. Okay, because neural network is a very powerful tool to build a data-driven model, nonlinear data-driven model based on process data. For neural network, we have a different type of neural network. For example, like a multi-layer feed-forward network. So that's the most commonly used approach. And also we can have other type of network, like wavelet-based neural network, mixed node neural network, autoregressive neural network, and recurrent network. So this recurrent network is a very powerful tool for building this dynamic model, which can provide accurate long-range prediction or multi-step height prediction. So this slide just shows some neural networks. Actually, in Newcastle, we started the neural network research quite a long time ago. So I think we started this research on neural networks in the late 1980s, early 1990s. Okay, so at that time, so we had an international neural network club, so joined with Professor Tom McVoy at Maryland University in USA. So at that time, we have this, I think this, so each year there were two meetings. So one in USA, in Maryland, another one in Newcastle. So actually, we in Newcastle, we are the one of the early research group in to do this research. So this figure shows this multi-layer feed-forward neural network. Okay, so you can see you have input layer, you got the hidden layer, and there can be more than one hidden layer and output layer. So the information flow in this forward direction, so it's called feed-forward network. This one is most commonly used neural network in applications. So this one shows this locally recurrent neural network. You can see the hidden neuron output feedback with input through a time delay unit. So this one, this recurrency can introduce this dynamics into the network. So this one is very useful to build a dynamic model to provide the multi-step height prediction, long-run prediction. And also, we also worked on this fuzzy neural network. So it's a combination of fuzzy logic and the neural network. Okay, so it's like So in this type of model, so we decompose the process operation into a different local operating region. So within each local region, we use this local linear model, build a model. So that model is only valid within that region. So we use those membership function, fuzzy membership function, to indicate the membership, for example, at the current operating point. So the membership of the current process operation belong to different operating region, and then you use this defuzzification to combine the contribution from those different models. So another work we did is this bootstrap aggregated neural network. So this one is quite a powerful approach to build a data-driven model, because when you build one neural network model, because the limitation in the process state and also limitation in the network training, etc. So when you just build one neural network model, so it's difficult to get a perfect model. So because you may not have a sufficient data to build this model, and also when you train the network, it may convert to local minima, etc. Okay. So here, to overcome this problem, so instead of just build one neural network model, so here we can build quite a lot of those neural network models, and then we combine those to form one model. Okay. So actually, this the principle is quite easy to understand. So it's like if you got a sensor, if you got a sensor to measure temperature, so that sensor give you this measurement error. Okay, so for example, if you measure temperature, so this thermometer can give you, for example, 0.5 degree of measurement error. Okay, so if you just got one sensor, so that one sensor always give you this bias in the measurement. Okay, but if you have a lot of those different thermocouples, different thermometers to measure temperature, so some may give you may give you the measurement higher than the true value, some give you measurement lower than the true value. Okay, so you got some positive error, some negative error. So if you take the average, if you combine those, so the error will reduce. Okay, so by combining those a lot of those imperfect models, so we can improve this model accuracy and the reliability. So actually, we did this work late 1990s, and also when Professor Zano Ahmed doing his PhD, so his PhD is on find a different approach, advanced approach to build this stacked neural network. So nowadays, this deep learning is getting popular. So one of the deep learning is called this deep belief neural network. So actually, this one is you have quite a few of those hidden layers. Okay, so you got deep structure in this network. So this type of deep structure is considered to have a more powerful nonlinear representation capability. Right. Okay. So now let's look at slow feature analysis. So slow feature analysis is also a relatively new technique in machine learning. I think the first paper on this slow feature analysis was published in early 2000. So they use this technique for I think initially they applied this to for example, speech recognition. So the idea of this slow feature analysis is try to discover only slow features in the signal. So for example, in this speech signal, so you got this, you got the noise. Okay, you got high frequency noise in the signal, and you got this low frequency. So those will mainly represent the useful feature in the signal. Okay, so the aim is to transform a set of input into latent variables. So those latent variables are slow varying features. So here we try to extract those slow varying feature, because this high frequency varying feature typically are due to the noise. Okay, so we ignore this high frequency feature in the data. So mathematically, it's an optimization problem. So basically, we try to minimize the first order, the variance of the first order derivative. Okay, and subject to those constraints. So the first constraint is okay. So the mean of the slow feature is 0. Okay, the variance is 1, and the different slow features, they are uncorrelated. Right. So the procedure to determine slow feature are summarized in this slides. Okay. So the first step is to normalize the date to 0 mean unit variance. Okay. So basically, you need to normalize your date into 0 mean unit variance. Okay. And after that, there's the second step is called the sphere or whiten. Okay, so in this step, you try to remove this underlying correlation. Okay, so you convert this x into z. Okay, and then the third step is you carry out single value decomposition on the covariance matrix of the first order derivative of this sphere signal. Basically, this sphere, this second step is try to right. So basically, it's try to you scale the date by the variance of the by the eigenvalue. Okay, so it's like so for example, it's like in the principal component analysis, when you get your principal component, you can see that your first principal component has the largest variation, and second one has the next largest variation. So basically, when you so for example, if you have a three-dimensional date, so when you get your three principal components, you will see that it's more like so it's not like a sphere, so it's like ellipsoid. Okay, so in this whitening procedure, so you try to scale your date by this by the eigenvalue. So basically, you try to make your ellipsoid into a sphere. And third step, we carry on this SVD on this on the covariance matrix of first order derivative. Okay, and then we can work out slow feature using this equation here. Okay, so basically this so now you can see we work out the first order derivative. Okay, we try to find out the slow, because first order derivative represents the rate of change. Okay, so we try to discover the slow change in this slow varying feature. Okay, we find this from the first order derivative, we find these slow features. So this numerical example just summarize or this how we perform this slow feature analysis. So for example, here we generate a date of those four variables: x1, x2, x3, x4. Okay, so here although there are four variables, but you can see from this equation, you can see there are two driving forces. One is a sine t, another is a cosine 5t. Okay, so we clearly can see this cosine 5t has higher frequency than this sine t. Okay, and then we add on those noise. So those noise are normal distributed with a 0 mean and 0.5 as variance. Okay, so you can see with this the noise is of a much higher frequency. Okay, so from the date you can see so the driving force are this sine t, slow varying, and then this cosine 5t, this you can see that this cosine 5t has a 5 times higher frequency than sine t, and then we have those noise which are of a much higher frequency. Okay, so when we apply, so here we got those x1, x2, x3, x4. Okay, so now we try to extract the driving force of this signal. We apply slow feature analysis. So after applying the slow feature analysis, so we have this the first slow feature, which is the most slow varying feature. Okay, so now you can see this one. So basically, it's roughly this sine t. Okay, so that's the first driving force. And this second slow feature, you can see it's given by this plot. So it's roughly like this cosine phi of t. Okay, so now you can see this first and second slow feature. So basically, they can represent the driving force within your signal. Okay, so now you can see with a slow feature analysis, so we can extract the true driving force. And the third and fourth slow feature, you can see they are just like the high frequency noise. Okay, so we can ignore those high frequency noise by using slow feature 1, slow feature 2 as the key component of the signal. Right. Okay. So now, so we propose an approach to combine slow feature analysis with a neural network to build a soft sensor model. So, so here we extend this slow feature analysis into dynamic slow feature analysis. So it's just similar to this dynamic PCA and PCA. Okay. So here we expand this the original date by the time lagged value of this date. Okay. So you can see here the first column represent this xt plus 1, etc. Okay. And then the next one will be like xt minus 1, xt. And then here the last one is xt minus d. So basically we add the previous d values of this measurement. We expanded the matrix into this expanded matrix, okay, to include this dynamic of the date. So, and then we apply this slow feature analysis to this expanded date matrix, okay. And then we extract slow features, and then we use a slow feature as the input to the neural network. And then we train the neural network, so the neural network can predict these difficult to measure quality variables. Right. So in this slow feature analysis with neural network for soft sensor is shown in this diagram. So the paper is published last year in this computer and chemical engineering. So that's your process date. So x1, x2, xn. So those like your pressure, temperature, flow rate, etc. Those are easy to measure process variables. Okay. And then we apply slow feature analysis to those easy to measure process variables, and we extract this slow varying feature. Okay, so here this dimension of the slow feature m is typically much smaller than this n and the original date. And then we use those slow feature as the input to the neural network. The neural network predict this difficult to measure product quality variables. So how to select the dominant slow feature? So here we use an approach similar to in this principal component analysis. So how to select this the number of principal component. Okay. So here we plot this eigenvalue. Okay, we plot the eigenvalue. So now you can see this. So the first slow feature has the lowest eigenvalue because it's the most slow varying. Okay, and then so now you can see in this plot you can see that after, for example, after using 6 slow features, then this eigenvalue jumped to a quite high value. Okay. So actually those high eigenvalue represent you got a large variation in this first order derivative. So those are the fast varying feature. Okay. So we focus on the slow varying feature. So in this case, we can based on this plot, so we can select 6. So 6 represent this like this elbow, or there's a gap in this eigenvalues. Okay. We keep the number of slow features as 6 in this case. Right. So now let's look at the applications. So here, In this case, we build a soft sensor for melt index in a large-scale industrial plant. Okay, so the process considered in this case is from a petrochemical plant in China, which is called Panjin Petrochemical Corporation. So the feed to this to the process contains propylene, hydrogen, and catalyst. Okay. And also we add on this a copolymer is added, feed into the fourth reactor when the copolymer is produced. In this polymerization process, so one of the important variable, product quality variable is called melt index. But this melt index is quite difficult to measure online. So in this in the actual process, the melt index is cannot be obtained frequently like other process variable. Okay. So for different grade of the polymer product, so they have a different melt index. Okay. So here we need to know the melt index in order to determine if the polymer is of the right grade or not. So here, to control this melt index, we need to have a frequent measurement of this. But because this melt index is difficult to measure, okay. So here we build the soft sensor. Now this picture shows this the diagram of this polymer production process. So you can see there are two CSTR and then two fluid advanced reactor. Process. So here we have a set of process operational date covering 31 days of plant operation. So actually during this it's like 1 month. Okay, so during this 1 month period, so there are several grades of different products were produced. So measurement of melt index in the two reactors were logged every 2 hours through laboratory analysis. So basically, in that particular period of operation, so they take this polymer melt index through laboratory analysis every 2 hours. Okay, and so the process variables are logged in a much higher frequency. Okay, but in the data we got is like every half an hour they have this process variables. But in the actual plant they have a more, so they have much more frequent than half an hour. But the data they give us is so actually they downsample those to half an hour. Okay, but half an hour is much frequent than this 2 hour sampling interval for this laboratory analysis. So for those 31 days of process operation, so we divide the date into 3 sides: training date, testing date, and unseen validation date. So basically, the purpose of training date is you train the neural network model on the training date. Okay, but because when you build your neural network model, so you need to determine the neural network structure. For example, how many hidden neurons in the hidden layer. So to determine the network structure, so we need this testing date. So basically, we try different number of structures and test the network on the testing date. So the network structure give you the lowest modeling error on the testing date. It's considered to have the right amount of hidden neurons. So we use that network, and then so once you build your neural network model, so we need to apply this the final neural network model on this unseen validation date to see how well this neural network perform on this unseen set of data. Okay, right. So here we build a dynamic soft sensor model represented by this equation. Okay, so here we have 30 process variables like temperature, flow rate, pressure, etc. Okay, we got 30 such variables. And so here we use those 30 variables at sampling time k, and then we add those 30 variables at the previous sampling time k minus 1 and k minus 2, etc. So finally we have those 30 variables at time k minus d. Right. Okay. So now we apply slow feature analysis to this set of data. Okay. So you can see here. So that's the first slow feature. So you can see this one vary with much much low frequency. Okay. And then this one is a second slow feature, which vary at a higher frequency than your first slow feature. And then you got your third slow feature, fourth slow feature, etc. Okay. Right. So now we use those slow features as input to a neural network, and we build this self-sensor model. This table compare this slow feature and the neural network with some other approach. So the first one is just build a single neural network model. Okay. And the second one is we use a principal component analysis on the data, and then we use the principal component as input to a neural network. So it's a PCA neural network. The next one is a partial least square regression. Okay, so PRS is like a linear model. Okay, and then the next one is a slow feature regression. So this slow feature regression is you discover slow features. Okay, and then you use a slow feature as the input of this linear regression, multiple linear regression model. Okay, so now you can see when you compare those different models, you can see this slow feature with a neural network. So this one gave you the lowest error on this unseen validation data set. Okay, so you can see this one perform the best on the unseen data. And those are the hyperparameters, like D is the number of time lags used in this model. So this one, this plot compare this slow feature regression. So use a slow feature and a linear model. And this one is a single neural network model. So you can see for those model, you can see there are like at a certain point there are quite large error. Yeah, right. Okay. So this table shows how to determine the number of slow features. Okay. So using this script plot, so we find this number of slow features is 17 in this case. And there was another approach proposed by earlier researchers. They use slowness of the input reconstruction. And but using that approach, we need much more number of slow features. We need 59. But you can see the root mean square error with this approach is higher than we using this script plot. So that's a second application. So here we we build a soft sensor for an industrial debutanizer column using slow feature analysis and neural network. So actually this process is shown in this diagram. Okay, so the debutanizer column is this one. Okay, so this one shows this the enlarged picture of this process. The date is provided by this reference. Okay, so in this reference, this one is a book. Okay, in that book, they provide the date, the industrial date for this process. So actually, my student just use this date from this reference to build the soft sensor model. Right. Okay. So there are 7 input variables to the soft sensor. So for example, like temperature, pressure, flow rate, temperature at to the bottom of the column at the 6 tree. Okay, so those are the soft sensor input, and the soft sensor output is a built-in concentration. Right. Okay. So those are the 6 input variables. Okay. So now you can see there are quite a lot of noise. Okay. You can see from this plot, you can see the signal are quite are quite noisy. Okay. And this one is the normalized built-in concentration date. Okay. So here we use this set of date, and we partition the date into 40% for training, 20% for testing, and the remaining 40% for unseen validation. So the soft sensor is given in this format. Okay, so we use the 7 process variables as input, and then we also add on the time lagged measurement of those 7 variables. So you can see here we use the 7 variable at time k, and then the 7 variable at time k minus 1 until time k minus d. Okay, we use those as input to the soft sensor, and we apply slow feature analysis. So here you can see we extract the slow varying feature. You can see slow feature 1. You can see this one is much smoother than the original signal. Okay. Now you can see if you compare slow feature 1 and slow feature 6, you can see clearly slow feature 6 got more like a time variation. Okay, because slow feature 1 is the most slow varying feature. So here we use those as the input to the neural network and build the soft sensor model. Okay, so once again we compare this slow feature and the neural network with some other approach, and once again on this unseen validation date, this slow feature analysis with neural network give you the better performance, the lowest root mean squared error. So here you can see the time lag is 10, number of slow features is 18 in this case. So this plot compare this slow feature analysis with neural network and principal component analysis with a neural network. So clearly you can see with PCA and the neural network, you can see here, you have a quite large error here. Okay, but with a slow feature and neural network, the error is much smaller. And this diagram shows this slow feature with a linear model. Okay, slow feature regression. So now you can see that this one you can see is not as good as the slow feature analysis with neural network. You can see the error here is quite large. Here got quite large error compared to the previous slides here. Okay, right. And the number of slow feature selection is based on this 3 plot. So we select 18 slow features. Okay, and using slowness of the input reconstruction, then we need a much higher number of slow features. But you can see the performance is not as good as right. Okay, and also we also extend this slow feature into a nonlinear slow feature analysis using this kernel approach. Okay, so actually we just published a paper in Journal Process Control just a few months ago. Right. Okay. Finally, to summarize, so in this talk, we can see that timely measurements of quality variables are important for product quality control. And to overcome the problem of quality variable that cannot be measured like frequently, so we can use a soft sensor. So soft sensor is an effective approach to overcome the unavailability and the hardware sensor. And so advanced data-driven modeling and the machine learning techniques such as neural network, deep learning, slow feature analysis can be very effective in building soft sensor models. Okay, so thank you for your attention.
Thank you, Dr. Che, for your presentation. I think it's very, very interesting and very kind of fundamental of modelings. I think those who into it will be much easier to understand. Those who more toward application. Sometimes can be very difficult to understand the thing, but it's okay. Toward the end, the soft what you call it, SFA give a good kind of results as compared to normal or conventional feed-forward neural network and everything. So I open for questions, guys. Any question to Dr. J? Any question from the audience? You can turn on your can unmute and you can throw your questions to Dr. J. Or maybe I will ask first, Dr. J. I would like to ask you about because from that graph when you show me the PCA analysis, right?
Yeah.
It seems like you utilizing the normal kind of a PCR analysis. Then you have a numbers of PCA, and then you stop in that particular graph, and then you use that as part of the SFA. Is it similar like that, or you have a different kind of selection as compared to PCR?
Right. Okay. So the selection. So actually here you can see. So we show this plot of eigenvalue. Okay.
Yep. Yep.
So it's quite similar to in PCA. You show this. So how much data variation is represented by each principal component.
Yeah. Correct.
So now you can see. So here we select. We try to find this turning point. Okay. So that at that turning point. So it's indicated if you select more slow features, so you are taking into a lot of noise into the data. So actually we stop at the turning point. So that's one approach. And another approach I didn't mention here, but my student tried this is to use cross validation. So basically it's like similar to in this principal compound regression. So sometimes you use cross validation. So basically you try different number of principal components, and then you look at performance on testing data. So here I also ask my student to try on this using this cross validation approach. So basically you try different number of slow features and then look at performance on testing data. So that approach is also fine. Okay, so sometimes also give you good performance. So basically you can
yeah, because maybe one other question from myself before I open to the rest. Because it seems like the SFA is utilizing what we call data reductions or to reduce the dimension of the data, right? Because you mentioned about the latent values, the eigenvector, eigenvalue, and everything. So seems like there is other tool that can support the SFA instead of just PCR or PCA, like they have like LDA, those kind of data reduction or So can we use that one as well?
Yeah, you can. Yeah. So basically, because this neural network is a more general tool for nonlinear modeling. Here we just use slow feature analysis with a neural network, but you can also apply slow feature analysis with some other like tools. Okay, so for example, you can use a slow feature analysis with, for example, you mentioned the LDA linear discriminant analysis. You can also apply with that one. So I think this LDA may be more for classification. So for example, in process monitoring or process for diagnosis, so maybe you can use a slow feature with some other clustering techniques. So it's more useful for process monitoring and for diagnosis. And you could also use a slow feature analysis with some other like a data-driven modeling technique, for example, like supporting vector machine and extreme learning machine, etc. Yeah, I think you can also use a combined slow feature analysis with some other like modeling techniques.
Okay, right. Okay, I open to the rest. Guys, do you have any questions? You can write if the question in the chat box if you want to. Then I can read it for you. Or you can ask directly to Dr. J.
Good morning to Professor Zainal and Professor J. Thanks for this wonderful sharing experience. So I'm from the industrial background. So for people like us in industrial, this is something, we know this thing exists, but it's not widely used. So it's now with this exposure may help us to explore more and then collaborate with the industrial hardware provider. That means we are run the plant. So we want to know how the industrial automation can help us on going to this direction. So no doubt this is good, but more exposure and sharing, it makes us more enthusiastic to know this is workable to us. We know this there is a benefit, but more on I would say on workable to our side, because there's how much we have to change, how much we have to explore. That is the next step we need to go. Anyway, thanks for this session, Dr. Zainal and Professor Jin. I'm
Okay,
glad.
thank you for the question. Yeah. Yeah. Okay. So good question. Okay. So like from industrial, I mean, practitioner point of view. So basically, you are interested in how to apply this in the actual plant. So I think with the actual industrial application, I think there are like some other, I mean, additional problem we need to address. For example, when you apply this for rural industry, so actually for example, from our experience, so if you got data from industry, so sometimes you need a lot of time to, I mean, to pre-process the data, because the data from rural industry, there can be a lot of like, for example, outliers, a lot of, for example, sometimes we got missing value. So basically, I think this, you need, well, first of all, you need to pre-process your data. So just, for example, you need to screen your data, I mean, detect any outliers. So basically, you need to clean your data. So actually, those take a lot of time. So once the data is is cleaned, and then we can apply this approach. So basically, you cannot, for example, to get a set of industrial data, just apply this approach. So basically, you need to first of all check the data from industry, because the data, I mean, from rural industry, typically there are like you got those outliers, those missing values, etc. So basically, you need. I think the first step to, when you apply this technique to industry is that you need to pre-screen the data from industry, pre-processing data from industry. So basically, try to detect find any outliers. You need to remove those outliers, and if there are any missing values, so you can either, for example, just remove those samples with missing value, or you can use some other approach, try to estimate the missing value, to fill in the missing value. So I think the data pre-processing will take some time for real industrial like data application. And also, I think for industrial application, so probably like we need like a collaboration between academia and the industrial practitioner, because I mean, so now you can see when you apply those techniques, so there are like some, for example, some steps like so how to select the number of slow features, and also in the neural network, so how to select the, for example, the network structures, the number of neurons, etc. So actually, those also need some expertise. So maybe the academic researcher maybe got more experience on. So for example, how to select the network structure, neural network structure, and how to determine number of slow features, etc. But the industrial people may have more experience on how the process behave, and so probably like I mean the combined expertise from industrial practitioner and academic researcher is a key to a successful implementation.
Okay. In addition to this argument, Jay, because you show us the block diagram, right? I think the hardware part, because we are the academic, we are not really into it on the hardware part, right?
Yeah.
You show us a couple of case studies from the MI, the melting index and everything. So you covering the hardware, or you have like additional team to covering the hardware things, and then you just focusing on the modeling and something like that?
Right. Actually, we just focus on modeling. So we just like you can see, I mean, this application we got data from So in the first application, we have data from this chemical plant, petrochemical plant in China. So we got this the set of date. Yeah, actually, the date. I mean, actually, we also initially did some data pre-screening. So just check the date to detect any outliers. So I think this. So actually, the 31-day operation is like we selected like a period with a relatively clean date. Okay, so without any outlier. I mean, occasionally there are some outlier, but we already treated those data. So hardware sensor. So actually, at this time, we are not dealing with hardware sensor. We just assume that, I mean, in the plant they have those hardware sensors. So we just like I mean, assume that the industrial people they have their expertise in selecting this type of hardware sensor.
All right. Okay, there's one question from the chat box from Dr. Jobran. The question is, SFA utilizes slow features, so can the method capture fast dynamics? For instance, some processes are multi-scale in terms of time and dynamics. Jay.
Right. Okay. Yeah, it can. So, for example, if you look at so in this application, you can see in the slow feature, you can see, for example, here in this one. So actually, the first slow feature is most slow varying feature in the date. Okay, but clearly you don't want the very high slow feature, because that, I mean, that one will be mainly noise. But you can see, for example, here in this case, you can see like for example, slow feature like 5, 6. So you can see those has fast dynamics than your first and second slow features. So probably those may represent like the fast dynamics, but the later slow features probably will be just like noise. So maybe like, for example, in this numerical example, you can see, so for example, in this numerical example, yeah, in this numerical example, you can see, so clearly like those very fast, I mean, slow features, those, probably those will be just like noise, probably like you're not like going to get any useful information from those very high slow features. In this case, you can see that so the first slow feature represents the most slow varying feature in the date, and then this one represents this, for example, this fast dynamics in the process. But actually, those are very high slow feature, so probably those are not useful. Those will be typically like noise.
Okay, maybe last question from the participants before we end our session for today.
Yeah, Professor Jainal, I have a question for
Yes,
Dr. G.
Dr. Agus.
Yeah,
Please.
yeah, Dr. G, good morning in Malaysia.
Yeah, okay.
Good early morning in UK. Yeah, thanks for your presentations. In fact, it's my privilege to see you, even though virtually. I did read a lot of your papers when I started my PhD some times ago. So yeah, I have a couple of questions. Maybe the first question is on the can say is the training time, or possible computational load for the online application of for your proposed method. So when we did something to Nonlinear and integrate something, normally the one that very sensitive is on the training time and on the computational load of the applications. Do you have anything to say about the computational load?
So the training time. So typically, from my experience, I mean, the training time is not is actually, well, in many cases it's not the issue, because the training typically, I mean, the training is so training is done offline. So for example, like you build your neural network model, so this training process is done offline. So once you train your neural network, so that one, when you apply this network for this soft sensor online application, so during this online application, actually you don't need to train this network. Okay, but sometimes you may, for example, in some cases you may want to like I mean, online retrain of your neural network. For example, For example, if there are any like process operational drift, so you want to in that case you could adaptively train your neural network model. So in that case, maybe there are some other approach like this extreme learning machine. So actually that one can be trained very quickly, because that one, in that extreme learning machine, you don't train the input layer weights. You just take random value as your input layer weights. You only train the output layer weights. But that one can be done using like this one step, like a regression type approach. And you could like combine this recursively square and apply this to an extreme learning machine. So actually, at the moment I got one PhD student. So we apply this, we combine this recursively square with extreme learning machine. So actually, that can be done very quickly. So just like the very traditional like this adaptive modeling or this recursive estimation. So in that case, you can get this, you can train this extreme learning machine, very less time. So basically, that one can be done online without any problem.
Sure. Maybe my last second question is on how this SFE neural net deal with the missing measurement. Have you done some modification to tackle the missing data?
Right. Okay. So the missing data, so actually, as I mentioned earlier, so missing data problem is typically during this data pre-treatment stage. So the missing data typically, so in our experience, so it depends on like the type of missing data. So for example, if you have quite a lot of variables, but you only get, for example, only like one variable have some missing value. So in that case, sometimes you could use this the correlation structure among those different variables, and you could estimate the missing value based on some other variables. So in that case, you could fill in the missing value. Okay. But in some other cases, if it's not possible to estimate the missing value, then in that case, probably like the common approach will be just like delete that sample or those samples with missing value from your data.
Yeah. Thanks, Dr. G. Over to you.
Okay, thank you.
Thank you, Dr. August, for your questions. And I think we come to the end of the sessions.